Hello everyone, my name is Donghoon Kwak from DGIST in Korea. My presentation is about real-time detection of foreign substances in seaweed using Pushbroom Hyperspectral imaging. Nowadays, the process of detecting foreign substances in food is mostly automated. And this is one of the most important processes in food manufacturing and distribution. In the case of seaweed substance detection systems currently used in the industry, RGB image-based or metal detectors are most popular. The RGB image-based detection system is difficult to distinguish between foreign substances having a color similar to seaweed or foreign substances outside the visible spectrum. But hyperspectral camera can distinguish between foreign substances having a similar color to seaweed. That's why we are using a hyperspectral camera. You can see the Korean dried seaweed and hardware configurations in figure 1 and specifications of the hyperspectral systems in table 1. We propose a foreign substance detection system that performs high-speed inspection in real time through simplified pre-processing and calculation using spectral features. Seaweed is a mixture of various materials, and the surface is uneven, causing severe diffuse reflections. Due to these characteristics, various spectral values are acquired even within the same seaweed. And you can see 80,000 pixels of seaweed spectral values in figure 2. We compared performance using 3 pre-processing methods: per normalization, max normalization, and reflectance normalizations. In general, when processing hyperspectral images, the reflectance normalization method using a white reference is popularly used. This is because the effect of the light source is minimized so that the spectral characteristics of the sample can be viewed more accurately. But in this case, per norm is most effective. If you look at table 1, excluding the 500 nanometer to 700 nanometer section, which increases in value depending on the degree of diffuse reflection, the deviation between pixels have been significantly reduced while maintaining the spectral characteristics of the remaining sections. Before detecting foreign substances, I think the seaweed and conveyor belt must be accurately sorted first, and you can see the spectral value of conveyor belt after per norm applying in figure 3. This method is to subtract the 503 nanometer value from the 742 nanometer value among the pixel spectral percentages. This is because the difference between the spectral values of 503 nanometer and 742 nanometer of the conveyor belt was small, while the spectral values of seaweeds have a large difference between the 500 nanometer and 742 nanometer values. And then classify seaweed and conveyor belt through threshold setting using subtract values, and classify the remaining values as a foreign substance. Second stage is a method of comparing the spectral value of the area classified as seaweed in the first stage with spectral value of seaweed reference data in 1-by-1 matching. It is possible to detect foreign substances that have not been detected in the first stage. Lastly, the display color is converted to increase the visibility of classified data. Seaweed turns black, the conveyor belt turns white, and the foreign substance turns red. The experiment showed 92.5% accuracy, and it was confirmed that real-time operation is possible even in 330 fps high-speed inspection. Thank you for watching my presentation.